Podcast, where we talk with the people behind the current events and breakthroughs in brain implants in an understandable way, helping bring together various fields involved in neuroprosthetics. Here is your host, Ladan.
Hello, everyone, and welcome to the Neural Implant Podcast. Today's guest is Andrew Trask, and he actually reached out. He wanted to be on the show, and it's a little bit off topic, I think, but he talks about deep learning. And so this is kind of a more general, broad view look at deep learning and what it means. But he does have some really interesting stuff there. He's doing his Ph.D. at Oxford, and his work is basically about anonymizing data. So I think that's very, very interesting for a lot of people who are worried, who are working with data, who are worried about, potentially private thoughts and everything like this getting out there. So this was a very interesting look at things. So yeah, this is a kind of more general overview, but I think it will be useless nonetheless, and we will talk on the other side. So Andrew Trask, pleasure to have you on the show. You wrote a book, Grockking Deep Learning, and so you're like an expert. It's funny because you're like an expert on deep learning, but also you've been doing it for kind of a short time, and you actually, in this book, you wrote like, within 18 months, I was like one of the leading experts in the field just because the field is so new. But yeah, do you want to introduce yourself, and what does grokking mean?
Nice to meet you. And yeah, so Grockking Deep Learning is certainly designed to be a quick introduction to the fundamental concepts of deep learning. And I do think that it is possible to become an expert in the field much faster than many other fields. 18 months is perhaps a little bit of an aggressive timeline. And I think that the real goal of the book and really, so grokking, the term grokking is really about an innate understanding, and more than just say sort of memorizing the concepts, memorizing definitions, but having an internal kind of gut feeling and intuition about how these systems work. And I think that it is possible to develop that gut instinct for what tools to use in what contexts in a relatively short period. And that's what sort of the 300 pages in Grockking Deep Learning is all about.
Yeah, I found it really cool. It's like, I don't know if this is going to be offensive, but like Idiot's Guide to Deep Learning. And it's really nice. It really, with the basics, like you don't have to have advanced calculus or something like this to go through it.
Yeah. That was, by all means, that's exactly what we were going for. I think when we first started setting out to write the book, the big hole in the field that was missing was an intuitive guide like this. There's lots of resources that mostly introduce it from the math notation standpoint. I think in the beginning of the book, we talk about this a little bit, that math notation is a great way to teach concepts to the extent it's very concise, it's very precise and specific. However, you have to already be extremely familiar and comfortable with that sort of language in order to be able to download new concepts quickly. And there's a lot of people that want to get into the field of deep learning that may or may not be that comfortable to be able to just read a formula and instantly grok what it's all about. And to truly do deep learning in industry and in practice, you don't necessarily really need to know a lot of the formal proofs and mathematical derivations behind deep learning. And so it just seemed like there was a really good reason to have a better resource or a simpler resource that cuts straight to the high-level intuitions that people often bring from mathematical formulas while sort of dancing around that as a strict requirement to learn deep learning.
Okay. And you're a PhD student at Oxford. So why did you think that you were already qualified to do this? Or why did you bring it upon yourself to do this?
So actually, when I first started writing the book, I was not a PhD student. So I had previously written an intro blog series. So imtrask.github.io. And I had a handful of posts that just did particularly well. So there's one called a neural net in 11 lines of Python that I actually originally wrote because I myself didn't feel like I really understood the guts of deep learning. I've been doing deep learning industry for a couple of years, and I had been using common tools. The tools of the day were Theano was the big deep learning framework. But you always interact with these high-level interfaces and these high-level libraries. And I found it very frustrating and annoying that there was a certain opacity, there was a certain barrier between me and what was actually happening under the hood. And so I went online and I found like an implementation of the deep neural network. And then I stripped out everything. I deleted as much as possible and got it down to just the 11 lines of linear algebra that it takes to train a neural net. And for me, that was a moment that really clicked. Everything became apparent because it wasn't hidden inside of this object-oriented sort of, I hesitate to use the word mess, but this object-oriented sort of shield that, while it's convenient and does lots of stuff for you, if you don't actually know what's going on under the hood, I think it can be a real barrier to making progress and to really understanding what's going on, especially when something goes wrong in a deep neural net or you want to do something a little bit novel. And so, when I put together this post called A Neural Network in 11 Lines of Python, it was really for my own benefit And I think it resonated with a lot of other people. And then I wrote a few posts along those lines after that. And then Manning Publications reached out and asked if we wanted to do a book in a similar style. Actually, that kind of gets back to what I mentioned before. Instead of teaching it with math notation, which some people know is like a language some people know how to speak, we taught it in terms of short Python snippets, which lots of people know how to speak, right? And you can actually run it and make sure that you're speaking it correctly in some ways. And you can take it apart and look at individual pieces, whereas math notation just on a page is a little more difficult to play with in that way unless you're very comfortable with standard math transformations and arithmetic and algebra.
Yeah, exactly. I would say definitely like it was all in, I guess, like Python. Like you could test everything out. You could throw in the code and see what's happening. I'm a bit wary of code and I don't really like it. But, I saw like, yeah, that definitely is better than the math notation. So deep learning is kind of like, it's a subset of machine learning, right? I found this actually really interesting. And even on this show, I've kind of used machine learning, deep learning, and AI interchangeably. But what's the difference actually?
Yeah, so machine learning is a class of algorithms that allow systems to learn, right? So it includes calculating explicit probability distributions and sampling and SVMs and all a huge class of algorithms that are statistical algorithms that are designed to be able to learn patterns in data. Deep learning is a subset of those that are loosely inspired by the human brain. And they typically take the form of simple matrix transformations. They're often a bit over parameterized. But yeah, so it's a parametric model. So it means it has a fixed number of weights at the beginning of training. And so I guess they're loosely inspired by neurons firing in the human brain. And there's sort of two things they're really known for when deep learning was first coming about. So first is that they were one of the first algorithms to really construct or have evidence that they were constructing a hierarchical view of the world, meaning that the first part of the algorithm, if it was, say, processing an image, would learn how to recognize sort of edges and corners and lines and curves and these kinds of things. And then the second part of the algorithm that consumes the output from the first part would take that information about edges and corners and lines and learn simple shapes and textures and maybe combinations of shapes and colors and shadows. And then the consumer of that piece of the algorithm would then use those shapes and edges and textures and corners to try to understand what objects are in an image, right? And so you have this sort of hierarchical layering effect. The really fascinating part was that you could actually train this end to end. I mean, you could learn all these layers all at the same time. So at the same time that you're learning what do edges and corners look like, you're also learning what objects are in this image and things like that. And it led to some massive breakthroughs in quality. So one of the first big breakthroughs was state of the art in image classification. And since then, it's far and away beat sort of the next best algorithms in the machine learning space. And then it has since gone on to break, I guess, the state of the art records in machine translation and in various game playing. So like chess and Go. Honestly, a plethora of other sort of state-of-the-art benchmarks. And so it's a very exciting field. I think the funny part is that we don't necessarily have a theoretical understanding of deep learning as well as we do for some other machine learning algorithms. But empirically, it ends up doing better on a lot of these benchmark data sets, which is very exciting.
So deep learning is more hierarchical, parametrized data that kind of like shuffles through and finds things the best way. What's AI and what's machine learning? Machine learning is just kind of like iteratively going through anything, or I guess what's the difference between that?
Oh, so deep learning being the smallest of these three categories, then machine learning more broadly includes deep learning as a subset, but also includes other machine learning algorithms that might try to learn differently. So, for example, if I were to try to learn whether the presence of clouds in the sky is likely to predict whether there's rain, like I could just go through and I could just count the number of times I see clouds in the sky and the number of times it rains and just look for direct correlation. That's a non-parametric model. Like that's a sort of a simple statistical technique. And we could call that a form of machine learning, right? But the deep learning, on the other hand, initializes a large random function and then sort of through trial and error tries to predict something, right? So in the book, we talk about this 3-step cycle: predict, compare, and learn. You initialize basically a very large and random function. So it's randomly initialized. You send an input in the one side of the function and you get the output, right? So an input might be an image and an output might be 5 outputs of the function that choose whether it's a cat, a dog, a bird, a fish, or a pigeon, some label set, right? And then if the classifier, this model, misses, so if it should have predicted dog, but it actually predicted a cat, then you'll go back into the algorithm, into this random function and say, how can I slightly tweak this function so that next time it's more likely to predict dog instead of cat, right? And then basically by doing this over and over and over again and slightly tweaking the function over and over and over again, eventually it gets to the point where it gets pretty good at recognizing dogs and cats. And this is a totally different way of learning than, say, just counting and looking for direct correlation between two things or some of the other machine learning algorithms that are out there. So this is sort of machine learning and deep learning. And then I suppose more broadly is this field of artificial intelligence. Some people will say that all machine learning and deep learning is a subset of AI. I don't necessarily take this view. I think there is some statistical analysis that would not necessarily be a part of artificial intelligence. Just in my own personal opinion, like just collecting statistics about something is not necessarily trying to create like an embodied agent with thoughts and feelings and knowledge of its surroundings and these kinds of things that
Trying to kill Sarah Connor.
yeah, or X other movie you'd like to reference. But yeah, so deep learning and machine learning are really kind of the guts of how people are at the moment trying to build sort of artificial intelligence. But artificial intelligence is a bit more of a goal and kind of an embodiment of many different pieces of intelligence that form a cohesive agent, right? They can interact in an environment, whereas sort of machine learning and deep learning are sort of like, how do you find patterns in data, if that makes sense?
Yeah, that's really interesting. Actually, that distinction is really, I guess, useful. I think I'm going to use it in the future. So yeah, neural engineering, neural implants, they're basically, we're looking at huge, huge amounts of data. I mean, I'm talking about like terabytes and terabytes. And in this case, and then we're looking for spikes. We're looking for different, like situations where, oh, okay, did the neuron just spike or was that some kind of other like motion artifact? Would something else happen? And so is it better to have tons of data? I mean, like, I think one of my previous guests likened it to something like, oh, we're streaming 11,000 Netflixes at once, like per second. So is it better to have tons more data or tons less data? And do you have to have like the answers to that data? Or can it be like open-ended, like, we don't know if it spiked? Or do you have to like be like, okay, it spiked at this time and computer, you learn what's the case, why that did it?
There's two different questions there. So the first one is it better to have more data or less data? So by and large, there's a thing called sample complexity. The sample complexity says it measures how many data points does an algorithm need in order to be able to learn a pattern. So some challenges like learning to play tic-tac-toe might have a really low sample complexity, whereas maybe a more complex game like chess or Go might require, hundreds of millions or billions of examples in order for us to learn it. Similarly, in healthcare, like being able to predict whether a doctor's note mentions cancer somewhere, it might have a really low sample complexity, whereas the example that you gave of being able to recognize complex patterns and spiking within a ton of signal in the human brain might require a large amount of samples. So this notion of sample complexity is actually extremely important. And I think you can summarize a great deal of the research that goes on in AI and machine learning as trying to reduce sample complexity. Because as it turns out, we have algorithms that can theoretically learn any pattern. So they're Turing complete. But the problem is that the sample complexity for more complex things, say understanding the brain, is so high that we just don't have enough data and compute power to process that much information to be able to find the pattern. So a huge amount of research, and perhaps even the majority of research in deep learning and machine learning, can be summed up as how do we bring that sample complexity down? So to answer your question in short, more data is always better. However, the context for that is sometimes the amount of data that would be required to fully understand a pattern is so great that it's not actually within the confines of what we can handle from a compute standpoint or what we can even gather from like a data gathering standpoint. And this is where model development and new forms of neural networks, new forms of machine learning models are trying to address. They're trying to make it so that maybe in the future we won't need as much data and we can get much smarter models given the limited resources that we have available.
Yeah, definitely. I mean, it could be like, oh, this motor neuron is like wiggle your ear, but you don't have sensors hooked up to the ear that you know if it's been wiggled or not. So it would just be kind of like dead in terms of this data, right?
Yeah, so that was the other question that you asked, which is it sounds like you're referring to labeled versus unlabeled data. So I might just have tons of brain scans, but I don't know what any of them represent. Or I might have, here's a picture of a brain when someone was tickling the ear, right? Or here's a picture of a brain when someone was watching a scary movie or something. So as it turns out, in pretty much every field, we have way more unlabeled data than we do labeled data. So obviously, it's preferable to have labeled data. And in most of the breakthroughs that have led to sort of real world applications have involved some kind of labeled data. Sometimes it's adversarially generated, but I would still say that can be quite labeled. But a huge amount of effort is also going into being able to learn about the innate structure of the world, even when we don't have labels. So to answer your question, we want to be able to do both. If you do have the option, obviously it's much better to have large amounts of highly granularly labeled data. But there are algorithms, especially in the deep learning community lately, like generative adversarial networks, that have been able to do a tremendous amount of things, even with data that doesn't have any labels on it.
Wow. Really cool. Yeah. I mean, I guess it's always preferable to have labeled data. I guess for the last thing, before we started recording, you were talking about securitizing data and I guess anonymizing data. And so in this field, obviously reading people's thoughts or like what the actual neurons are firing can be a huge intrusion into privacy. There's been a lot of concerns about this. And people have talked about anonymizing the data, which is akin, I mean, what I understood is kind of like shredding the information, like putting it in a paper shredder. But the thing is, I've also heard that computers are really good at this. And FBI, I've seen in a few movies, they like actually have gone through like shredded bins, like shredded paper bins and like put it together. I mean, it's very painstaking work, but computers don't mind so much. They don't complain. They don't take overtime. So they can piece together that anonymized data and make it unanonymized. So you've been working on this actually for a PhD. Do you want to explain this a little bit? And is this still an issue? Could FBI come in and have thousands of people and look through the bins and piece together like, oh, whose anonymized data was what?
Yeah, actually, I love that analogy. That's such a good way of expressing it. So a huge tying back into what we just talked about. So as you can imagine, if we don't have algorithms that can train on small amounts of data, then data becomes a real bottleneck to progress. And unfortunately, it's not just that we don't necessarily collect enough data. It's that even when, say, hospitals collect data on certain brain scans or certain medical treatments, often they aren't willing or able to share that data in a safe way such that then someone can train on data from 100 hospitals or 100 research centers as opposed to just one, right? Which could give us maybe an algorithm that's 100 times smarter, right? Or however, depending on how you measure intelligence. And so a huge potential for further progress in understanding these deeply personal areas of humanity, like the human body and the human brain, is can we figure out ways to be able to share intelligent information in a way that keeps that information secure and makes it so that when people are dealing with this information that they can't, as you said, reverse engineer the outputs to try to then infer personal things about the inputs. And there's been a tremendous amount of progress in this area over the last few years. And there's 3 specific algorithms that I think are worth mentioning that perhaps people have not yet heard about that I think are going to totally change the landscape of how research on private information is done. So I think the best way to sort of talk about this is just to consider ourselves in the context of trying to do some sort of study on, say, the brain. So to use the example that you gave, right? So across a myriad of different hospitals, individuals are sitting down with patients and they are recording scans of their brain and asking them questions and gathering data, right? So this is happening in the real world, today and yesterday and across time. And so us as the researcher, now we go, okay, I want to be able to study this to predict, let's say, aging in the brain. So actually, I have a friend here at Oxford who actually tried to do this very recently. So she wanted to be able to use deep learning to predict how old a brain was given a supervised data set that just says, here's pictures of the brain, here's how old the patient was. And the idea was that if an AI model could learn what in the brain looks like aging, then we could actually perhaps have some information that would be useful to trying to counter that and try to understand how we could potentially reverse or change the impacts of aging. So here we are. We have this challenge. Now, using naive tools, tools of, say, last year and the year before, standard deep learning tools, perhaps like PyTorch and TensorFlow, this would first require you to go to all these different hospitals and say, hey, here's the study I want to do. Give me a copy of your data, right? Send it to me. This is an extremely daunting process. It's very expensive. Many people are simply just going to say no because it's so deeply personal data.
And I mean, honestly, it could be illegal too.
Oh, yeah. And in many cases, they have to say no because of legal restrictions, just like you said. And this doesn't just affect researchers. This affects hospitals, enterprises that are trying to build new products and services. This affects even more so startups who have no data to start with at all. Like you want to do a radiology or a brain imaging startup, like the first 6 months to a year is just going to be trying to get access to enough data to build your product or service, right? This is before you even get to product development or sales or marketing or VC. And they often have this chicken and egg problem where in order to get data, they have to have customers, but in order to have customers, they got to have the product done. So yeah, anyway, in enterprises, in research, and in startups, this barrier, this zero start problem, it's absolutely huge. But the first class of algorithm for privacy preserving machine learning really makes huge strides in this. So it's called federated learning. And what federated learning is a new kind of tool that basically says, instead of having to go to all these different data providers and say, hey, give me a copy of your data and bring the data to wherever you're going to train your AI model, wherever you're going to do your statistics. Instead, we want to bring the statistics out to the data wherever it already lives. This really changes the dynamic of the request, right? So it says, instead of saying, hey, give me a copy of your data, give me the ability to do basically whatever I want with your data, right? Because when you give a copy to someone, they have no guarantees that you're not going to copy it and send it somewhere else, that you're not going to continue to move it, that you're not going to lose it, like all these kinds of things, right? It's a huge ask to ask for a copy. But instead, with this federated learning idea, you can actually send statistical models into someone's organization, which will learn a small amount of information, say just how to predict the age of a brain, right? And only that predictor will come out. Only statistical information that is relevant to making that prediction leaves the organization, right? So the idea is that instead of me asking the organization, hey, give me all your personal medical records, tell me what does Bob's brain look like and how old is Bob, right? Those are the input and the output that I need. Instead, I want you to allow me to glean information of what does aging in the brain look like in general, across all humans, right? And this is very aligned with the researcher's interest. The friend of mine that works on this has no interest in individual people's conditions, in data points. What this researcher is actually after is, in general, across humans, in humanity in general, what does this pattern look like? And federated learning allows a researcher to extract just this pattern without ever needing to actually see any of the data the statistical model is run on.
That is really interesting, actually. Like, I didn't really, I guess, understand it when you explained it before we started recording, but this makes a lot of sense. Like, okay, you don't actually ever see any of the data. You just kind of put in little virus or something. I mean, maybe people might be a little bit worried about like, hey, what are you installing into our servers? But yeah, that's actually really interesting. And then you only get that certain piece of data out. So you wouldn't be able to reconstruct anything from that, right?
Man, that's the perfect question to ask. So there is a question of, okay, exactly what statistical information is leaving, right? That's the next natural question. So really in partnership with this first class of algorithm called federated learning, which is really just about distributing the computation so that the computation can happen over a large number of servers as opposed to just in one location. The next sort of class of algorithms is called differential privacy. And differential privacy is a set of formal proofs whose chief goal is to be able to make the claim in the context of when partnered with federated learning of, okay, the statistics that are leaving your organization, I can prove with this degree of certainty and various tunable parameters, but a formal mathematical proof that the statistics that are leaving your organization, statistical information that's coming from your database to me, has no personal private data. And is this formal proof and these formal guarantees that really activate federated learning for use on intensely private data. And you might be wondering, like, how does this work? How does an algorithm tell the difference between public and private information? Well, the trick that differential privacy uses is it looks across records from multiple different people, right? So let's say we have brain scans from 100 different people, and there are going to be different statistical things that it notices, different patterns that it notices across these 100 different images. And so what differential privacy says intuitively is that if there's a statistical pattern that I see in, say, all of these images, right? Well, that statistical pattern must not be unique to any of them. And if it's not unique to any of them, then it's not personal information. So, and this follows from the intuition that stuff that's personal to you is actually going to be unique to you, like your first and last name and date of birth, social security number, like these patterns that only have an occurrence of once is private information. However, if it's a pattern that is across many different individuals, as some statistical feature it's across many individuals, then it's more, in this case, reflective of something that's a part of the human condition. So if I were to say, like, one pattern would be like humans have 2 arms and 2 eyes and 2 legs. So an algorithm going in and learning that humans have 2 arms and 2 eyes and 2 legs would not be personal information, right? Because it actually observes this statistical pattern happens in all of these different data points across individuals. That's sort of an intuition on how differential privacy makes the decision on whether or not a piece of data is personal or private. And the cool part is that we can partner this with federated learning so that a researcher not only does not see the data that they're studying, right? Because it stays inside the organization that owns data, but they can have formal proofs that guarantee that any information that's leaving has a certain degree of repeatability across individuals, right? Is not personal or specific to any individuals that are in their data set.
Okay, so I'm kind of wondering because if it's like a brain scan, or let's say, you're reading what neurons are saying, I mean, wouldn't each one by definition be a personal one? Or are you saying like pattern would emerge? So it's maybe talking about patterns like, okay, this pattern is unique to this person, therefore we should hide it. Or this pattern is not unique to this person, therefore we can publicize it, something like that?
Exactly. So another friend of mine was studying brain scans looking for basically when long-term memory and short-term memory is accessed. So he had a really interesting supervised learning data set. And so something would be unique would be a few brain cells firing in relation to one particular question. But if I see that the same set of brain cells fire when I'm accessing long-term memory across 10 or 20 different people, then we wouldn't consider that to be personal information, right? That's just how brains work. Does that make sense? So it's the difference between did John's brain fire on this question and do brains fire for this question in general? Does that make sense?
Yeah, that is actually, I guess, a good way to put it. So first layer is not taking any of the code. It's just putting in your own code and getting some systems out, some algorithms out. Second layer is seeing like, is this generalizable or is this not? And depending on that, extracting it or not. And there's a third layer too. And we were talking about, this is actually what you're working on for your PhD, right?
Yeah, it's really bringing all three of these together that makes it possible. So the third one is called secure multiparty computation. And really the problem that it exists to address is that the nature of these first two require that the statistical model, the AI that's going down to the data to learn, is kind of put at risk. So let's say that I'm trying to train a $10 million brain prediction model. So it's got significant commercial value or some other reason that we would want to keep it secret. And so the thing about this is that if we send the model down to an individual, the problem is that someone could perhaps steal that model and someone could take it and use the IP for themselves, like if it happens to be particularly valuable information. And so we want to be able to actually perform this analysis while still protecting the model in the process. And the way that we do this is we actually encrypt the model using encrypted computation, such that when we send the statistical model down to an individual's data center or someone's smartphone or whatever data set we're analyzing, that it is in an encrypted state. It's in a protected state while it's down there. So it's sort of a one-way information gateway, so you can learn about things, but no one can sort of learn anything about it, if that makes sense. And the way this happens is, I think, quite intuitive. So secure multi-party computation, I think the formal definition on Wikipedia is that it's a function where you can evaluate, two parties can evaluate the output of a function while keeping the inputs private. But I think a more intuitive explanation of it in the context of AI and machine learning is around shared ownership of a number. So I can take the number, say 5, and I can split it into two shares, 2 and a 3. And this 2 and a 3 then is protected, like it's encrypted. I can give the 2 to someone named Bob, and I can give the 3 to someone named Alice. And if Bob and Alice have these two numbers, then neither of them can necessarily know what number was actually encrypted. So, Bob, by looking at the 2, doesn't know that the actual number that was encrypted was a 5, and Alice, by looking at the 3, doesn't know the number encrypted was a 5, right? However, Bob and Alice can still perform arithmetic with this number. So let's say they wanted to double it. They wanted to multiply it times 2. If Bob multiplies his number by 2 and Alice multiplies her number by 2, then the 2 will turn to a 4, the 3 will turn to a 6, and the sum of them turns into 10. Right? So we just took our 5 and we multiplied it times 2 and turned it into a 10. And the cool thing here is that this computation, this arithmetic, was able to happen while the number was encrypted between Bob and Alice. And as it happens, AI, machine learning, deep learning, statistics, an AI model and a data set are both just large collections of numbers. And the inner workings of these statistics are simply large collections of sort of arithmetic and simple functions. And so the cool thing is that then we can actually perform training these statistical models while the model is in an encrypted state in this way.
Wow, that's really cool. Yeah, so they can be absolutely sure that nothing will be coming out. So it kind of reminds me of that game is you guess a number, you add 5, subtract 3, whatever, divided by 5, and then you subtract, at the end you subtract your own number, and it's like, did everybody get a 2? And it's like, whoa, and it blows, 8-year-olds love it. So that's kind of what that reminds me of. So this is a really nice primer on deep learning. If people want to learn more, how do they do that?
Yeah, so obviously Grockking Deep Learning is a great place to start. I think the next place to sort of learn more about deep learning is perhaps by picking up one of the major deep learning frameworks. So in particular, like fast.ai. So if you go to a website, fast.ai is a really great place to learn a framework called PyTorch, which I think is a really intuitive way to learn about deep learning. And I think that's sort of a good progression of learning about these different concepts. So first learning the kind of the fundamentals in a book like Grockking Deep Learning or one of the other resources, and then going and jumping into sort of a framework like PyTorch or TensorFlow. is probably the best progression. And then after that, it's just a matter of jumping into projects and trying to tackle, various machine learning problems.
Sounds good. I hope people will start doing that in the neural engineering, neural implant space. I don't want to do it though. It's too much programming. Andrew, do you want to talk about OpenMind a little bit?
Yeah, I spent a great deal of my time as part of an open source community called OpenMind. And our real goal is to take these 3 privacy preserving technologies that I was just mentioning and lower the barrier to entry for adoption, with the general goal and the long-term goal of promoting privacy preserving, secure, and value aligned AI. And the way in which we do that, there's a group of about 3,500 people in the community and around 200 people that contribute code. And we do 3 things. So we raise awareness by doing podcasts like this and articles and blog posts. We create educational resources. So we create tutorials and courses around how to actually use these privacy preserving technologies. And then we spend a great deal of time building open source tools that are sort of Apache 2 licensed and freely available to use inside of the existing deep learning frameworks. So we extend PyTorch and TensorFlow in particular with secure multiparty computation, differential privacy, and federated learning, so that people can sort of, with limited retraining, simply augment their use of existing deep learning tools and use them in a privacy preserving way. So yeah, at openmind.org, highly recommend checking it out, and think that we're a part of this year's major change towards privacy preserving deep learning, which will also unlock vastly more training data to solve some of the most important and personal problems that AI and machine learning can be applied to.
And I hope after today, there will be a neural implant tab as well.
Yeah, you bet.
Okay. Andrew Trask, thank you so much for coming on the show and teaching us about deep learning.
Yeah, sure thing, man. Great to meet you.
Hey everyone, hopefully you enjoyed that. Yeah, I found that interesting. I was a little bit skeptical. Okay, do I publish this? Do I not? Before, but I think it turned out pretty good and I'm happy with it. It was a nice primer overview of deep learning. And I especially like the part about when he talked about the differences between AI, deep learning, and machine learning, because I've always used those interchangeably. And I guess they're not interchangeable. I also really like the private security, privatization, securitization of everything. And I think this could be a good way forward. Some of this stuff, I don't know if it would necessarily add too much more security or if it would be that much more useful for people in our field, but it could be good nonetheless. I'm not an expert in this, so I don't really know what is the thing that, regulators are trying to protect us from, or what the regulators want to prevent. Yeah, so I found this really interesting. Check out his book, Grockking Deep Learning. I have a discount code, and if you write me and you're one of the first few people, then I might be able to get you a free copy. Just hit me up and I'll get you this. It's really interesting. Like I said, it's kind of a idiot's guide to deep learning. And if you're really interested in this, then you can definitely look into this. Also, check out his OpenMind. I think this will be really interesting, especially if we get some kind of a nice neural implant community going on over there, then I think that would be really, really cool. Anyways, hopefully you enjoy that. And let me know what you think. Was it good? Was it good to have something like this or not? Should I have just, established professors and business people on the show, or is this kind of general overview helpful sometimes? Okay. Until next time, this is a Neural Implant Podcast.
Hope you enjoyed the show and were able to learn something new, bringing together different fields in novel ways. Until next time on the Neural Implant Podcast.